Hello, everyone. Thank you for standing by. As a reminder, this event is being recorded and will be archived on the shopmag.com. And if you look at your screen, we have a poll question up for you. We'll give you a few seconds to click your answer, and then we'll get started. Okay, hello. I'm Jeff White, editor of The Shop. Welcome to today's webinar, Smart, Safe, and Ready to Work, Power Inverter Basics for Fleets and Upfitters, sponsored by Go Power Dometic. Power inverters are the backbone of mobile power, quietly transforming DC battery energy into AC electricity needed to run tools, equipment, and critical electronics on work trucks, service vans, and specialty commercial vehicles. As fleets and upfitters push for higher productivity, safer operations, and reduced idling, inverters have become essential components of modern mobile power systems. This session introduces the fundamentals of how inverters work, why design and quality matter, and how to select, size, and integrate them effectively across different applications. Our presenter today is Sean O'Connor. Sean has been at the forefront of adapting mobile power to vehicles for decades. He currently leads commercial and professional vehicle sales for Dometic's Mobile Power Solutions segment, partnering with fleets, OEMs, and upfitters on safe, reliable onboard AC power. He's leading the charge in clean energy initiatives worldwide. His experience and passion for renewable energy continue to drive power solutions that benefit both the environment and the industry. At this time, it's our pleasure to begin the webinar, which will include a Q&A session at the end. You can send your questions through the Ask Question box, and we'll get to as many of them as possible. Now let's turn it over to Sean to begin the presentation.
Thanks, Jeff. Appreciate that introduction. Hello, everyone. Hopefully everyone's here to learn about inverters. The next slide here, I'll skip past my introduction slide with my mugshot here. So just looking at the results of our poll here, looks like we have some with low knowledge, a lot with moderate, so that's great. I think this is going to have something for everyone, and maybe by the end there's another poll, and we'll see what your knowledge is by the end of this presentation, and hopefully everyone has high knowledge by the end of this. So we're going to go through, it's going to be mainly about inverters, but we'll talk about a little bit of different power conversion equipment in there as well that's totally relative to installations and to power inverters themselves and things that we can use to help them out. The company I've worked for the last 27 years has been around for 30 years, which is quite a long time in the alternate energy business. There's a lot of newer companies out there, but we've been around for a very long time. I've done it for most of my life. So yeah, we're celebrating 30 years making products, so we're very proud of that. This slide, it's probably the slide I'll spend the longest time on because this is pretty much going to link everything we're going to talk about for the rest of this presentation. So I like to use this analogy when talking to anyone, no matter how much experience they have with inverters or solar or anything along those lines. So battery, it's so important. The batteries in any of these alternative energy applications or any CPV or trucking application, the battery is like your gas tank. The battery's rated in amp hours, and amp hours are just like gallons of gas. So if your battery's a gas tank, amp hours, it's going to have a gallons of fuel it can hold. And if you have more batteries, you hold more gallons of gas. Then when we're talking about the inverter's just like the engine in your car. It's consuming gallons of fuel to run devices. So with an inverter, you might have your power tools, your compressor, things like that. Depending on the size of that load, it's drawing a certain amount of gallons of gas per hour out of your gas tank. Then we have the battery harnessing or the wiring just in general in the system. It's like the fuel lines in your car. If you have this big V8 muscle car and you put too small of fuel lines in it or installed too small of fuel lines, and you went to hit that accelerator to the floor, the engine's going to sputter out, not perform like it should because it's not getting all the fuel it needs into the engine. So harnessing is important. We'll go through all that as well and how you size it. Then voltage. This is very, very important, and it's often overlooked. And this is actually the reason we have so many power problems in all industries, including the trucking and last mile delivery and whatnot. So voltage is like the pressure at the gas pump. And the best way to explain it, if I buy a brand new vehicle and it has a full tank of fuel, and I go drive my 400 miles or so, if I pulled up to a gas pump and it didn't have enough pressure in it to fill that tank back to 100% full again, I clearly can't drive as far as when I leave that gas station. I don't have a full tank any longer. So we need to make sure we're bringing batteries up to a proper voltage to ensure we have great inverter and performance, because the higher the voltage, the better. And we want to make sure we're keeping the batteries unsulfated. And we can get into that later in the battery section, but you want to desulfate the batteries by keeping the highest voltage possible within the rating of the battery. Then the solar controller, I'm going to talk about solar just briefly because it's a great way to keep the batteries topped up. Solar controllers are basically like the fuel shutoff at the gas pump. If I pull up with my car, they have an automatic fuel shutoff. Once the tank is full, it stops filling it with fuel. It doesn't start spraying out of my gas tank. So that's exactly what a solar controller does. It's made so you never overcharge a battery. And then the solar is just like a gas station that's open anytime it's light out. And it's, depending on its size, will deliver a certain amount of gallons per gas back into your batteries. Another gas station would be the alternator on your vehicle. It's also sending power back to your batteries. And later on in the slides, I'll get into how the alternator, how we can get max performance out of that, or how we can use all of these different devices together to have a completely self-sufficient system. So what is an inverter? Jeff actually alluded to this already. An inverter converts battery power, generally 12 volt in North America, but you could do 24 volt batteries, 48 volt. We generally stick to 12, which is in most of the automotive industry in North America. We convert 12 volt battery power to 120 volt AC household power. So this is so you can run anything that you plug in your wall at home. You can run that out in the middle of nowhere if you have a battery that's charged up in your vehicle. There's two different main types of power inverters that you're going to see in the industry. There's modified sine wave and pure sine wave. The one on the right, the pure sine wave, that waveform just keeps going endlessly. It's a nice swooping wave. That is what all 120 volt devices are designed to run off of, and to run off efficiently. And as you can see on the left side, the modified sine wave is more squared off. It's not a smooth flowing line. And because of that, some devices run poorly off a modified sine wave. So why on earth do we still make modified sine wave inverters if the one on the right is an exact replica of AC, sometimes even better than you get out of the wall, and you have the modified sine, which isn't a perfect replica? The modifieds are always less expensive, and sometimes by a significant amount. So they're always going to be attractive to customers to use. Basically, if your load will run off of a modified sine, it's great to save the cash and go with a modified sine wave inverter. Some devices I've run across in my 27 years that have issues with modified. Microwaves tend to take twice as long to cook something as if you ran it off a pure sine. So that's twice as much power coming out of them. Cordless tool chargers, another big problem I see, where I've seen batteries getting damaged. So the lithium batteries are worth more than the tool half the time. So this is another place I don't like to go the inexpensive route and just go with a pure sine wave. But those are just a couple ones. And then inductive loads like a compressor, motors tend to run better off the pure sine than they will off a modified. So just a few examples there of how you'd make your decision. So this is just two of the inverters we make that you can get modifieds. Many people make them, and many people make pure sine waves. And I'll get into how you can choose these a little bit better. But again, going back to how the inverters work, they're the engine, if we're using our analogy, and they're consuming 12 volt power and turning it into AC household power. So a few things that you want to look at that matter for you: surge versus continuous power. It's actually changing in the inverter industry, and a way to reduce the cost of the inverter is not only to lower the surge, but you could lower the continuous. You can have a continuous for a set amount of time, and then as the inverter gets up to a certain temperature, it starts to derate. So that's something you're going to want to look at on a spec sheet. All the inverters we design actually just do whatever they were rated for continuous. They'll just run that 24/7, 365 days of the year. The surge power, a lot of companies just default and say it's double what the continuous rating is. With all the testing we do in our own lab, this is simply not true. A real surge power, they can get away with saying this because a surge, yeah, typically you could say it surges for 0.01 milliseconds at double the rating. But the real amount of time you want to run something to get a motor started, like a compressor, you'd want good surge power. You'd want at least 3 to 5 seconds of being able to handle that amount of power. So you'll notice our spec sheets, they don't just default to double the continuous power. And there's a lot of other companies that are reputable doing the same thing. If you look at it, they're quite honest. They'll say 3-second surge is X amount of power. And this is something where generally you can just look online, but motors, a lot of them will use double their rated wattage. And they'll all have a rating, a wattage rating on them, most devices. And it's usually double that for a very short amount of time to get these motors running. And compressor is probably the #1 culprit in the CVV market. And by the way, CVV is what we call it in our company, and it's commercial passenger vehicle. Basically covers all the heavy duty stuff and trucking for us. Manual versus automatic transfer switches. I'm going to get into the different types of inverters and inverters that aren't just inverters. But this is just something I'll quickly point out. There's a couple types of transfer switches out there. Why you use a transfer switch with an inverter system is you never want two sources of AC power. For instance, a generator and an inverter trying to power the same load at the same time. You will wreck stuff. If you're running shore power at the same time as a generator or an inverter, you will wreck the generator or inverter. The shore power will win every time. Shore power is grid power or utility power off the grid. So a manual switch, you have to go manually switch to change power sources. An automatic transfer switch will select between the two sources. And you usually set it up to have a dominant one that when it's available, it will use that. So for a generator, you might make the generator the dominant connection if you have an inverter and generator together. When you have shore power and generator, you usually make the shore power the dominant. So it will, because it's obviously not costing fuel or anything to run it. GFCI outlets versus non-GFCI outlets. This is another nice way to see what the quality level is on an inverter. Keep in mind, though, some of the GFCI outlets that you see in your bathroom, they're there for a reason. Anytime you have water or potential of water to be close to an outlet or get potential to go into your device, like a heat gun or whatnot, if you're working outdoors, you're going to want to have GFCI protection. And it will trip very quickly and save the person operating the device from being electrocuted. Non-GFCI outlets just look like regular household outlets. Please keep in mind, though, some people have their GFCI done internally. You have to look in the specs to see it. But some you can visually see. They have the GFCI outlet on it. Some of them, the GFCI is actually done internally. UL458 listing, we'll get into this, but this is a great way to weed out what's a quality inverter and what is not. To pass UL458 testing, there's shock and vibe to replicate what we're going to see in the trucking industry. You're going to see like reverse polarity protections. You're going to see things where we're not able to actually electrify the case of the unit or electrify a device that's being run from it. So GFCI outlets are part of that. It's just good. This is kind of sets a standard. If you look for this, you'll see a price difference for sure, because much higher quality components have to go into these. So it's a great way to weed out what's a cheap inverter versus what's something that has pretty good components in it and is safe. Oversizing versus adding, like here's the problem with oversizing. So I was actually just joking before this started that if you want to know, is the inverter large enough, and I'll get into sizing in a second here, but Some people are just going the biggest inverter they can get. And then they're like, there, I'm safe. Everything should run off this. It's a 3,000 watt inverter. It's 30 amps. The outlets in most of your house are just 15 amp. So it's a tremendous amount of power that you can get. But the downside is you need a lot larger cable. Like, and copper's not inexpensive these days. So you need much larger DC battery cables coming from the battery to the inverter. And just pretty much every part of it is more expensive. You're going to need a larger battery bank for it, and larger inverters, even when nothing's running, they have a larger parasitic draw. And that's just the idle draw. It's just sitting when it's left on, even with nothing running, it has a larger draw, which drains down your batteries quicker. So it is important to right size your system. And I'll show you how to do that in the next slides coming up here. Again, continuous versus surge. This is another thing. How can we size our inverter the right way? What should we be looking at as our way to figure out what the surge is and how we size that correctly? Or are we more concerned about continuous loads because the loads we're using don't have like a big motor to start? So these are just some common loads that I see in the industry. And you can see many of the items like test equipment, laptops, cordless tool chargers and stuff, even under 1,000 watts. Like 1,000 watts is plenty, but you need to keep in mind how many loads you plan to run at the same time. If you're planning to run your cell phone chargers, a laptop, the cordless tool charger, and a coffee maker, well, then you need to look at the wattages that will be listed on all of this equipment and make sure you add them all together for anything that's going to be running together. So we need to make sure the continuous rating is rated above what all those devices combined together would be. Then surge, it's more like when you have a compressor, that motor, the high motor, or even convection microwaves, they usually are double the rating of the microwave as well. So you could have a 1,000 watt microwave, it's convection, it actually needs 2,000 watts to get started. So the surge rating, like I say, induction loads. So a coffee pot, for instance, is not an induction load. It's a resistive load. It just heats. It's like the heater, a baseboard heater is a resistive load. An induction load is something with a motor in it. So a plug-in drill or the microwave or a compressor, they have motors in them. They're induction motors, and they have the high surge. And if you have more questions, I totally understand. And hopefully we'll have time at the end. We can go through those. I'm happy to answer those. So pro tip, this is the easy button to push here. If you can plug whatever you want to run into a normal outlet at home, which you can see in the image here, it is less than 1,500 watts, or that 1,500 watts will be enough power. It's a 15 amp or less load. So the coffee maker plugs into it. If your microwave runs off of it, you know you're within 1,500 watts, which makes the 1,500 watt. And now most people are rating them 1,750 to 1,800 watts in the industry. They're the most popular inverters. Usually a 1,500 to 2,000 watt converter are by far our most popular, just for this reason. You can plug into a normal outlet and you know it will run. All right, inverters that aren't just inverters. I'm going to explain the equipment, these different type of conversion devices, and then how they get put inside of an inverter, just for more convenience and an easier install. So we're going to talk about transfer switches, converters, the difference between a converter and an inverter, which is super frustrating how close they are in name, and then inverter chargers. So I talked about that transfer switch and the importance of it. We cannot have two sources of AC at the same time connecting to one another. So we have a transfer switch. Either you go out and you manually flip a switch, and now you can run the generator and it will run all the loads. Or you have an automatic transfer switch, and they're made in a couple sizes, 30 amps or 50 amp. And it depends on the service level that you're plugging into. A lot of the trucking side is still 30 amps plenty, but 50 amp I've still seen out there. It's a very different plug. It looks like your dryer plug. So you'll know if you have a 50 amp service that you're working with. Then we have just the difference between them, but we make only automatic transfer switches. We don't make the manual ones. It's far more convenient. You can have a standalone transfer switch. These get used a lot of the time in applications where you want to choose between generator and inverter, or sometimes you want to choose between the shore and a generator. But yes, you can actually stack two of these together to select between three different sources. So you could have shore power, generator, and inverter all connected to run the same appliances or devices. And you just have one transfer switch feeding to the next. And then that transfer switch would feed to the breaker panel or to the outlets that you're running. Charging, so converters. A converter is basically a battery charger. It takes 12 volts, 120 volts. So this is, I don't know if we put the 120 volt in here, but we take 120 volt AC and convert it to 12 volt DC. But a converter, the only difference between a converter and a battery charger is that a converter can actually directly run loads. This is very common in RV. So if you plug in at the RV park, it will actually run all of the lights and it will run the water pump and all these things directly. Instead of just charging the battery and taking power from the battery, it'll actually feed a lot of those loads directly. And we make these devices in 35 amps up to 100 amps, and you just select the size based on what you need to run and what it draws amperage-wise. So how many gallons of fuel does that device consume? So the converter, it's a battery charger essentially, but it can run 12 volt loads directly. An inverter, again, it takes 12 volt and converts it to 120. It does the exact opposite of the converter. So that is the difference. The converter, the charger, the inverter, taking power from batteries to give you AC household. So inverter technology, we obviously have the inverter on its own. We make in our new line of power inverters, we're doing 1500, 1800, 2000, and then 3000 watt. This is by far the most common. We do have smaller ones, not in our fancy new style. It's in our own old industrial sine wave ones, which are still great inverters, but we use those just for 200 watts for the, I think we have the 700 and we have 1000. And the reason we're staying with those, they work great. They're still quite efficient, but we've got even more efficient with this new line. And every gallon of fuel matters out of that gas tank or battery. So we're trying to draw the least amount possible out of there to still provide that same high wattage for you. And we're also wanting a lower idle draw. So if you leave the inverter on, we're trying to reduce that no load draw to the lowest we possibly can. Then we make an inverter with transfer switch, an automatic transfer switch inside it already. This is great for if you have a generator on board, or if you have access to just grid power when you maybe park your unit back at the yard. If you have access to AC power from another source, you can have it. So this is running the microwave, all your test equipment, it's running the cordless tool chargers. But when you run the generator, or if you plug in back at the yard, now we're not drawing any power from the battery, and we're just passing the power through to those same loads. And it's seamless. It's super fast switching, so the loads don't even notice that anything's changed. And we make those in a 1200, an 1800, and a 3000 watt. And they have a 30 amp transfer switch built into them. And doing this all in one is actually more affordable than doing the inverter with a separate transfer switch. So adding it all into one unit, it's just one box. It's a lot easier to do that, and it costs a little bit less for you. So we do make inverter with transfer switch, and so do other companies out there as well. Then we have the advanced inverter charger. So now we're taking a transfer switch, an inverter, and a charger, and in fact, a very efficient and high amperage charger, and putting it all into one unit. So we have a 2000 watt and a 3000 watt that have a 30 amp transfer switch in them. They're just single leg. These are probably our most popular right now. They have incredibly high chargers. So the 2000 does 125 amps with very little shore power. So only about 13 amps coming in. We can delve deeper into that in the questions if we want to, but that's quite efficient to only use 13 amps from AC and be able to charge such a high amount of current into your batteries. So for example, if you're running a generator, this means instead of using a 3,000 watt generator, you could drop down to only a 2,000 watt generator and still be charging incredibly quick and passing power through still to some of the loads. So we have a feature called Power Share on here, and that's specifically designed to allow you to use a much smaller generator and still run some pretty high power loads like big compressors or air conditioning units. What we do is for that surge, we actually draw power from the battery and provide extra power from the inverter to help the generator out. So this is allowing people to drop from like a 5 kilowatt generator to maybe a 3,000, or from a 3,000 down to a 2,000, even down to a 1,500 in some cases. So we can save on not only noise level of the generator, better fuel economy, and just more portable for you to carry it around. So that was a new feature that we put into the inverter charger called Power Share. We also make a 3,000 watt 50 amp service. So remember I was showing the transfer switch that can do 50 amp. This allows you to do dual leg. So you could do 240 volt power if you stack the inverters together, or we can just handle 240 volt input, and we separate the inputs so you get your full 50 amp service provided to your breaker panel. This is more common on larger equipment. 50 amps is a tremendous amount of power. It's really 100 amps service at only 120 volt. But yeah, definitely our crown jewel here, packing everything to one. And this inverter package, it's smaller than ever. We used to have one before. This is about half the size of the old inverter charger we had. So batteries, our gas tank, very, very important. And also the cause of poor performance through the whole system, especially with your inverter. The lower voltage you have of your battery, which is what you will see if you have a battery that's heavily discharged, it will have very low voltage. Like it could be 11 volts, it could be 10.5 volts, which I've seen very often. That's going to make the inverter work way harder to convert it to 120 volt AC. It's also going to have a much poorer surge performance and probably even a worse continuous output rating. So you're going to drop the output rating of the power inverter. So if it's a 2,000 watt, it might start performing like a 1,500 because the batteries are low and low discharge. This is super common. Like I said, we're using alternators to charge the starting batteries and auxiliary batteries in these systems a lot of the time. But a lot of these alternators are not super intelligent, and they're not charging the voltage, like I said, high enough to make sure we fully filled the gas tank again. So and I just want to point out, if a wet cell battery, like if you have low voltage, it means your battery's dead and low. If you drain a battery completely dead, so the inverters, like all of our inverters have a low battery shutoff set point of voltage. If you're hitting that constantly, we're cutting the life of those batteries in half, especially if it's a wet cell or an AGM. Lithium batteries can be discharged further, and we can get into that later on. But it's very important we keep these batteries at a higher state of charge. So how do we keep them charged, and how do we keep the batteries healthy? I am blown away at the amount of people going through batteries every 8 to 12 months. Like these batteries should be lasting at least 3 years if we're charging them correctly, if not more. So how do we do this? Well, the alternator is one of the ways to do this. Most alternators are fairly unintelligent, and they're just putting out a straight voltage. A lot of them even kind of hedge their bets and only charge about 13.7. I like to see a wet cell battery come up to 14.4 to truly desulfate and get the gas tank to 100% full. So there's devices you can put on to make them smart. You could put a DC to DC converter on it. This is helpful, especially if your alternator is very far from your battery. You can see a lot of voltage loss. So saying that low voltage can happen, especially if we don't use the right size wire, or if the wire is just very long, you're going to see a drop in voltage. Well, that means we're not charging the battery to its full state of charge. We're not filling the gas tank full. So very important. But yes, this is a very common way, and I highly recommend using multiple charging systems together to make sure we keep the batteries in a great state of charge. So we have our alternator, possibly a DC to DC. Another option, we can add solar to the equation as well. So this goes on the roof, obviously somewhere where we need exposure to sunlight. But the nice part, there's no moving parts to it. It's completely silent, and it's working whether you're there or not. As long as it has light on it, it's putting power back into those batteries. And its charge set point is to not stop charging till those batteries are at 100% full. So the gas tank is full, and now then we'll disconnect charge. So another nice alternative to keep these batteries topped up is solar. Then here's an example of using everything together. We have a device called the Phantom Advanced Trail Charger. So the Phantom will take the alternator charge and solar charge. It will choose solar first, so we're being as easy as we can on the alternator. So the less we can use that, the better. And we will combine that power, and we can charge not only one battery bank, but two. So we could charge a starting battery and an auxiliary battery. We could charge an auxiliary battery and a pallet jack battery. So it can charge 12 or 24 volt. It can charge any battery chemistry. So it's a great new product we brought out to try and solve these dead battery issues. But a lot of the time, some people are using inverters from this aux battery to charge the pallet jack. Well, that takes a lot of power. So we need to keep these liftgate batteries charged up as much as possible. But yeah, anything, you can still use a Phantom even if you only have one battery, but it's a great way of tying in the alternator and another source like solar all at the same time. And this is, the Phantom can do 30 amps continuous charge into your batteries. So installation and best practices. When I'm doing installs, none of the inverters are completely waterproof. We do conformal coating on all of the circuit boards and everything, so they can be in a marine environment. They can be, but we don't want direct water on them. We don't want it sitting above pools of water. You want it in a dry location. We want it preferably in a cool location. As I said, the higher the temperature goes, the lower performance you get out of the inverter. And a lot of inverters out there start to derate quite quickly as you get into these any ranges above ambient temperature, which is typically in the, like, I don't know, in the Fahrenheit, you're probably in the 70 to 80s. And if you get it above that range, you start to see derating. Our inverters typically go quite a bit warmer before they derate, but still, keep it in cool a location as possible. I've seen people ventilate them with fans as well, like little muffin fans, to help just get more airflow. But our manual has all of this information in every one of our inverters, by the way, but we try and leave at least 2 inches of clearance around the whole inverter so we have airflow to try and keep it cool. We try and say don't install the inverter in the same compartment as a battery, especially if it was sealed. And especially if you have a wet cell battery that gases. That gas is hydrogen gas. And inverters, when you first install them, when you connect the battery the first time, because the capacitors have a high inrush, you'll see a spark. And that spark could light hydrogen gas. If you accidentally laid a screwdriver across the terminals of the batteries or whatnot, or across the terminals at the inverter, if they were uncovered, you could have a spark. So that's why we try and say, please have it in a ventilated area if you're mounting them together. But many of the installations they're in larger compartments, and they will have the batteries and the inverters in a similar compartment, but you got to vent them. And then I always want my inverter as close to the batteries as possible, because the copper is expensive. A 3,000 watt inverter, I'll get into the wire sizes in a couple slides here, but the wire size for a 3,000 watt inverter is 4/aught cable, which is absolutely massive. Copper is expensive. That cable is expensive. All our kits come with a maximum length of 10 feet because we feel you should not go further than that, because you're going to have voltage loss, and then we're going to have poor performance. Cable routing, this is probably the most painful part of wiring anything, and whether it's inverters or solar or anything, it's just getting the power from point A to point B, and how do we do it efficiently? So we try and have, as I said, have it as short as you can, have the right gauge cable. If we're running through a firewall or anything, put grommets in, make sure there's nowhere where the wire is going to be rubbing and having a potential for a short. And then a lot of strain release and stuff. So if anything moved or anything got pulled on, we're not yanking things. The key is we never want anything to come loose. And I always recommend, after you've done an installation, go back 6 months later and retighten everything again. Things heat and cool down. So you've got expansion and contraction happening at all these connections. It can loosen things up. Loose cables will cause thermal events potentially, or just melting of things, because what you get is a bunch of friction and resistance. And anything with resistance gets heat. So you want all your connections as tight as possible. I always recommend going back over things after the initial install. A few months later, 6 months at the max. Obviously, we don't want sharp edges on stuff. We don't want, use a proper color coding, so it's quite clear what's positive, what's negative. On the AC side, what's hot, what's neutral, what is ground. We usually do bare copper for the ground cables to make sure all of that is clear to everyone. And then we're protecting from heat, vibration, and moving parts. Talked about ventilation already. Sorry, there's some repetitive slides in here. But we don't want to block the intake on not only the inverter, but if you add any other exhaust fans into it, that it's clear, because that just puts a lot of strain on the fans if they can't pull the air in easily. But we want to make sure, again, that 2 inches at least. The cooling is just so important just to get maximum performance. One thing I do want to mention on the cabling, you can use a fuse, and I'll get into our kits that come with the fuses, or you can use a breaker. The breakers are great because you can also disconnect the system if you want to work on it. So breakers are great. They're just slightly more expensive than the fuse only. The fuses we recommend, which I'll get into here, are fairly expensive, and they're not as easy as you would think to come by. So I like this going with a breaker because it's resettable. If you had a fault for whatever reason, someone made a mistake and accidentally shorted something out, you can at least reset the system. Fuses, a lot of our pro installers, I noticed they'll like zip tie an extra Class T fuse with the system and point that out to the customer. So if it did pop, you could replace it easily, especially if you're out in the field and you don't have to go looking for it. But I'll show you what the Class T fuse looks like in the next slide here. But yeah, you don't have to be 10 feet. If you can be 1 foot from the inverter, great. But speaking of the 1 foot, I always try and have my fuse or my breaker as close to the battery positive as you can. So you want to be within 1 foot of the battery if possible, because we want that to trip as close to our power source, being the battery, as possible. So great rule of thumb there, have that Class T fuse installed or the breaker as close to the battery positive as you can. EMI, it's electronic components, DC wiring. If you had it really close to something sensitive like a radio, yes, you could get some feedback and hear some static on it. One little trick, some people braid the DC cables to prevent it and make it a little bit less. But most, like I'm noticing most power sources and devices now are a little more high end, so they're not picking up the frequency as bad, but something to think about. And then grounding points, which I'm going to kind of show you in a picture here, how to ground the system to be safe and make sure we got a path to ground that is not a user. So here's that Class D fuse I was talking about. This goes generally in a fuse holder a lot of the time, but some people will actually put this fuse right on the terminal of the battery. Totally acceptable. That's as close as you can get to the source. But a lot of people, we sell an option that has, you just strip the cable and it slides in and has a screw down on each side. And so that's like our fuse block that has that. This is the fuse by itself. And as I said, our cables come with 10 feet. That's just our standard size because we figure that's enough for any application, and that's as far as you should go. And here you can see, we have this right on our website. You can find this, but you can see, here's the rating of the wattage. Here's the size cable we're recommending. Now, fun part about fusing, you are fusing the cable. You're not actually fusing the inverter. So if you put just 10 gauge cable, but you had a larger, like 1,000 watt inverter, first of all, the inverter's not going to perform. Like I said, the fuel lines aren't big enough. It's going to sputter, outperform, not perform. But you need to be fusing for what the cable size is. And I can quickly run through that. 4-aught cable is a 400 amp fuse. 2-aught cable, 300 amp fuse. Number 2 cable, we're dropping down to a 200 amp fuse. So it's all listed in here. We're trying to fuse for the cable because the cable is what will burn if you have a short. It won't be the inverter. The inverter is going to probably protect itself. But Class T fuses and a lot of good breakers, they trip so fast they protect the inverter as well, not just the cable. But most of our inverters will protect themselves. But other lower quality, you might, like having a high-end fuse is a great idea. All these warnings are in the manuals as well. But again, I already touched on the low voltage and that it's not going to perform well. We have low voltage shutoffs on all our inverters. Reverse polarity. I've embarrassingly enough done this myself. You've connected to the wrong terminals. A lot of our inverter line will give you a get out of jail free one time, but some of them don't, and a lot in the industry. It's actually an expensive option to build into an inverter. So that's another reason for where you see some discrepancies in prices between inverters. That's one of the ones to look at. Does it have reverse protection on it? Because it's kind of an expensive mistake if you ruin your inverter because you hooked it up backwards. Because most people who build inverters will put what we call a tattletale in, which tells us that it got hooked up backwards. And it's a device that will only blow if it sees reverse polarity. So grounding the inverter, very important. We don't have to read through all this segment, but here I do want to point out there is a mistake on this, and I should have caught it. The chassis ground, there's always a chassis ground lug on our inverters. So you're going to connect that bare copper wire to it, and that's going to run down to the chassis ground in the vehicle. And by the way, this is that inverter fuse block I was talking about where the cable ends can go into each side when you strip them down, and then it's just got a T-handle Allen key to tighten it down. So we have the chassis ground connected to inverter, but we're also going to do a chassis ground at the batteries. And this one's in the wrong position. This is actually the positive to negative connection, doing a series connection to make these two 6 volts 12. Chassis ground should be going on this side. It should be coming from this negative that would go to the inverter. It should be going to chassis at that point. This side is correct. Chassis ground would be coming off the negative connection again, near the batteries. I try and do it as close as possible to the batteries. And then I'll also have a chassis ground coming off the inverter lug right to chassis. Then we know we're safe. We don't have any potential of short happening on the DC end, although it's very safe at 12 volt. It's not really going to go through human skin. But the 120 volt side, very important because that will go through human skin and can shock you. Safety. Just want to delve into UL 458 a little bit. Way more credibility if an inverter legitimately has UL 458. You can even go online to see if the inverter model is listed with UL. Important thing to do because I have seen inverters come with UL 458 stamped on them, and then you go to look and they actually don't have it. So people are doing some sneaky things, especially on Amazon. It gets a little sneaky out there. You want to make sure they are actually listed, and you can ask people, I want to see your literature to show your inverter is actually listed. The regulatory approval, they have to go through a set standard of tests. So it's just showing you they're not putting cheap components in generally if they're able to pass the testing to get UL 458. There's a consumer trust, but then that safety element as well, where there's no danger of this thing electrifying the device you're running and electrifying you, which is obviously not something we want to have happen. So safety first. All of our inverters have UL 458 on them. And people always ask me, okay, what's the difference? Like, what's changing in these inverters? Why is one so cheap and then yours is more expensive than that? And there's ones even more expensive than you. It's usually features that they've taken out or just lower cost components they're going to use. And what the missing safety certification, that's your number one thing to look for. They can put cheaper build quality components in there, and that's where you'll see, like, as they heat up, they got to drop the output of the inverter quite quickly, so that's a good sign. So that's same with thermal derating Temperature sensitivity, kind of in the same boat. Obviously, higher safety risks are a concern. We don't want to have a thermal event. Usually, if someone has UL 458, it's been tested for that. They've even been tested if it caught fire, would it contain the fire that started inside of it to not spread it? So that's even part of the testing. So very important. A lot of them can be lower efficiency. So it just takes way more power out of your battery bank to accomplish the same task. And missing those protections like overload, like I said, reverse polarity, short circuit protections, things like that. And moving on to the kind of the future of inverters and where things are going and where we've chosen to go. And there's many others who are going this route. And what it's doing, making the connectivity better and making the devices communicate with each other, is helping us get to a spot where we can be as efficient as possible, whether we're charging batteries, pulling power from batteries, and running loads. How can we make some intelligent decisions using communication to lengthen the run time on the battery and speed up the charge time of the batteries? I had it explained to me before, communication. I'm going to talk about CAN bus because that's what we use. So we use CAN bus communication. CAN bus is like the US Postal Service. So that's how the letters are getting back and forth to each other. The protocols that you use are what language the letters are written in. We speak RVC, which is an RV communication standard, and J1939. RVC was based off of J1939. If I was going to explain it best, the J1939's English, and I'm really not trying to throw shade at J1939, we use it. It can do basic things like voltages, what's the temperature, what's the amp hours remaining in the battery. It can do those fundamentals. It's not able to report, and it will be able to, hey, I'm going to turn this device down because I'm not using that right now. It's not there yet. RVC is. So if we're going to say J1939 is like kind of a letter my young child might write, and RVC is maybe something adult would write. There's just way more going on in it. And that's because RVC wanted to be able to have the blinds draw and have it in the fancy RVs. So they had all these standards set for this way higher amount of intelligence and communication. But that's coming to J1939. And I know we're adding things all the time at the TMC level. So that's what I'm talking about when I'm talking about communication and how we do it. So why do you care about it? Well, 1939 is the wired connection. Connectivity through wireless, we usually do through Bluetooth in our devices. And sometimes we'll actually use a Bluetooth dongle that connects through our CAN bus to make something able to connect to your smartphone, to a tablet, and eventually through the cell phone, being able to update the firmware real time of all of our equipment. In, for example, the inverters, the smart inverters, to be able to give them new firmwares. We come up with new features. We can actually make the product become even better as you've owned it. So we're like, oh, we can make it more efficient by making a few changes. You connect it to your cell phone, it's got the new firmware on, and it loads it onto the firmware of the inverter. So really exciting stuff there with wireless and CAN bus connections. But again, the CAN bus, J1939, it's a wired connection to a physical display. So right now we just have a small 3-inch display, very affordable. The inverters only, it's basically an on-off switch because they don't have a ton of extra features where they need to worry about charging, worry about pass-through power, things like that. So generally just an on-off. It's going to give you what the battery voltage is and how much current it's using. So that type of stuff's going to come through. The advanced sine waves with the transfer switch in them, they're going to be giving you the power coming in. Is it clean power? Did you connect to a source that's got really dirty power? Maybe we don't want to be connecting to that and we'd rather use the inverter because we don't want to damage any of our sensitive electronics in the truck. So, and then of course, inverter on off. By the way, this display can act as the remote Bluetooth dongle. So this remote can be up somewhere in the work area where the inverter might be tucked away down below under some metal or like near the batteries. So we can use this as our remote display. So we can also use our wireless at the same time, Bluetooth on the app. Then we have the inverter charger. This is where you really get to utilize the connectivity, because we could back off the charger if we don't have a lot of input power coming from the generator. Like maybe we have a small generator connected. Pardon me, it's only 1,000 watts. No problem. We'll dial the inverter charger down so it never pulls more power than that generator is capable of giving us. We can dial down, pardon me, the output loads. You know what? I'm going to stop sending power to these because the battery, it's getting pretty close to low, and I don't have much power coming in, and I don't see an alternator charging at the moment. So the connectivity, it's not just on our inverter chargers or on this equipment. It's on our solar controller. It's on our batteries, which I'll talk about next. So the battery is going to be telling all of these devices what type of state of charge it's in, how long you have remaining. So you can see here, 2 days, 12 hours remaining, running what you're currently running. So this is just like going back to the car analogy. Our vehicles now tell us, hey, by the way, you only have 100 miles left before you need to fill up because you're going to be out of fuel. We're trying to tell you the exact same thing with your batteries. This is how much time you have left before you're out of power. This is just a closer look. I'm running short on time, and I want to be cognizant that I want to answer some questions at the end. So I think we're getting the idea of what the power track system does. Everything's talking to one another. We do these things all on one single board, so there's much fewer connections if you're an installer or an upfitter. This kind of takes away any of the guesswork. Everything's pre-wired. You're just connecting the batteries and the input and output to your loads, and everything else is taken care of for you. So this just makes your installations quicker and more efficient. But the batteries, like I said, very important. Now we make few types of batteries. We do AGM. We don't do any wet cells. We do AGMs, one of the best AGMs out there. We compared to Odyssey. We've done third-party testing. They look great. We can make our unintelligent batteries, which are the AGM, the lithium, intelligent using that power track system. We have a little shunt that comes with it. So it helps you make an unintelligent system intelligent, and it's not very expensive. So I just wanted to point that out. And then the advanced lithiums, they have all of that built into them. So these are the ones telling all the devices, listen, I got this long remaining, I need this much charge. I'm running this amount of power right now. So you can actually send me the maximum amount of current or gallons of gas per hour. Send all of that in. Where many batteries, the charging is being done by the controllers. So they're telling you what they want, what the controller is trying to do. It's usually trying to be safe about it. So this is a great way to be more efficient with charging. I apologize if you can see the fluttering of the light, because my lights just started to go crazy here. Last but not least, we are going to be at the Keystone Big Show and at the Gaylord Texan in Grapevine, Texas. This is our booth number. We would love for you to come by. Colin has been on the Q&A right now. He'll be with me. We are happy to go in more depth into this and answer more questions for you. But that is all I had. Does this, you have a second here to go in and answer your new knowledge level. Hopefully it went up, and we can take a look at the results of those, of the poll here, and then we'll get into questions. And if we're okay with going long, I'm free to go long as well to answer more questions if needed. But right now it's looking like we got about 7 minutes. I'll give you about, I don't know, 20 more seconds to do the poll. And I'm just going to turn my camera off and fix this light because I don't want to have a seizure here with how it's strobing in my face right now.
That's great. Thanks, Sean. We really appreciate everybody's attendance today, and there's a lot of great information in there. Again, if you have any specific questions you'd like to ask right now, go ahead and use that question box. Before that, Sean will take a quick look at the poll results.
I'd say that was pretty successful. We no longer have anyone with low or very low knowledge, so that makes me happy.
That's excellent. Absolutely. Yeah, we appreciate everybody's attention for sure. Yeah, I'm taking a look at the Q&A chat. We have one from Ian who asked, are there any options for running inverters in parallel?
Yes, great question. The inverter chargers are only model that can be ran in parallel. So that means if you had a 2000 watt, you can make it a 4000 watt system, or I'll just choose our largest system. So you can make a 3000 watt, have two of them in parallel and be a 6000 watt system. So great question.
Excellent. Okay. How about a recommended build sequence? If someone's taken on one of these projects from start to finish, where do you start? Where are the hangups? What's the different best practices you can give somebody to give them a head start?
Yeah, it's another great question. I always start with what are the loads I need to run, and try and have as much foresight as possible. And that's going to determine now, once we look at the wattages, and again, multiple devices together that will be run at the same time. What's that total wattage if I look at all their ratings? Is it 2,500 watts? Well, I should probably go with a 3,000 watt inverter. And then it also helps me choose my gas tank, my battery size. A 3,000 watt inverter, here, I didn't mention this, and this is important. A nice, easy way to figure out your gallons of gas used out of your battery. Whatever the wattage is, just divide by 10, and that's how many amps are coming out at 12 volts. So if you draw 3,000 watts of load, you're pulling 300 amps out of your battery. So if you had a 300 amp hour battery, in 1 hour, it will be dead if you're running all 3,000 watts. So yeah, I start with loads, then inverter, and then I try and figure out my battery bank based on how long I need that to run, the continuous. And I can also start to supplement and not do it just with gas tank. I can also add a gas station, being my solar. So I can add that. How many gallons does it deliver? And how many gallons will I get from the alternator? Because you know what? I'm usually driving an hour a day with my to and from. So it's just math. You're just adding those things together. We actually have sizing sheets on our website, and you can go in and fill it out. Here's all the things I want to run. Here's what they're drawing. And then this is the size. If I want, generally the batteries, I try to go with how many days do I want to go without any power coming in? And I usually use 2 days. Can I get by 2 days without running anything? I know I operate 6 hours of the day, and in 2 days, I'd use X amount of power. I hope that helps, but obviously budget comes into play as well. And another thing, a lithium battery, you can use all of its amp hours. So if I have a 100 amp hour lithium, I could use all 100 amp hours of it. If I have a 100 amp hour AGM or a wet cell, you usually should only use half of it if you want to get any type of decent cycle life out of it. So another great question, and a part I didn't have in the presentation, you usually want to draw AGM and wet cell batteries only halfway depth of discharge. So that's another upside. Even though lithiums are expensive, you can get twice the power out of one battery and a lot more cycles.
All right, so a lot of it's been focusing on, work vehicles and project sites and job sites, et cetera. What about powering homes, like for power outages or transferring power? Is this setup, conducive to that?
So you could do this, but you need a transfer switch at your house. Most people who do this will have a sub panel, so a lot less devices. You're not going to want to run everything because your home has probably 100 to 200 amp service at it. You won't be able to fill everything. So they'll pick select devices that are on the sub panel, and that'll be like fridges and some lights. Usually, some people it's the Wi-Fi router because it doesn't draw a lot, and then you still have internet. So if those things are on a sub panel, you'll have a transfer switch, and it can be an automatic transfer switch. And what we'll do is whenever it sees your truck get plugged in to the house, you'll have a specific outlet to feed that sub panel. More accurately, it'll be feeding that transfer switch. It will kick over, and now it will provide power to those. And then when power comes back on, you just go out, unplug or turn off your system in your vehicle, and now it's going to let utility power return to powering those devices.
Excellent. All right, we got another question from Dan. He asks, lithium ion versus lithium iron?
Yeah, great question. So lithium iron phosphate is all that we make because it's the safest battery. It doesn't have quite the battery density of lithium iron. It's actually got nickel in it. And that's what we have in our phones to be just the absolute best power density ever. But not ever. There's probably new technologies coming, but that's why that's used there. But they could be dangerous if you punctured them or whatnot. Most trucking applications are using lithium iron phosphate, and that's what we use as well. And it's LiPo 4 is what it ends up coming out as if you're looking at batteries. Or LiFePO 4, sorry, LiFePO 4.
Awesome. Great. All right, well, we're pushing up here at an hour. Let's do one final question. Just to summarize, can you kind of outline the actual differences that justify major price differences between products with seemingly equal specifications?
Yeah, the seemingly equal, that UL is a great one to weed out. Obviously, if you're looking at a modified versus a pure, it's going to look way less expensive. So get that figured out first. Then, yeah, does it have UL 458 on it? Very important. And just make sure, go on the UL site, make sure that actually is listed would be an important one. But you'll notice generally, like the ones who have it are in a similar price range. You'll start to look around and go, oh, there's that range, and then there's a totally different, much lower range, and they generally don't have all those extra things I was talking about, like lower quality components. You got potential of some shock risk. You might not have reverse polarity protections, things like that. Might not even have GFIs on it. So yeah, that's probably your best way.
Excellent. I really appreciate it. All right, Sean. Well, thanks for this presentation. I think it was extremely educational, and really appreciate everyone's time today. I want to let the attendees know that you can look for an email from us later today that will have a recording of this presentation. And you can always find all of our webinars online at theshopmag.com. So if you have any other questions or anything, use the feedback buttons, etc. As you see those, we'll get you some answers any way we can. Just want to thank everybody for joining us today. Appreciate your time, and have a great afternoon. Thanks, everyone.
Thanks, everyone. Appreciate it.